So in the previous lecture we took an example on multi-stage counter current extractor. Today we will take one more example on this, and here we will like to solve a problem related to minimum amount of solvent required. Okay, so in this case, if you recall, we have to look for del point, in fact del min point, where the tie line coincides with the operating line. And the good thing about this new example, which we will take into this lecture, is the trend of the tie lines. So the earlier this multi-stage counter current extraction, right. So and let's take a system here: pyridine, water, and chlorobenzene. So we have pyridine in water, which we want to remove using the solvent chlorobenzene. So this pyridine would be C solute, water is the feed, which we denote by A, and chlorobenzene is the solvent with B. Okay, and we have this multi-stage counter current extraction. So let's draw a couple of stages here, 1, 2, and we say the last stage is NP. Then we have this feed F, this extracts from E1. Then we have this R1, then this is E2. You have R2 and this E3. All right. So the extract coming to this stage is RNP minus 1, and we have the extract from here ENP. RNP the treated raffinate, and we have the solvent S. So this S or B, this is chlorobenzene. Okay, and the problem statement says the feed is flow rate of the feed is 2.25 kg per second, and it contains pyridine, also the water and pyridine mixture contains pyridine say 50% weight by weight. All right, and we have been asked to treat this feed using the solvent chlorobenzene, pure chlorobenzene. So we have this YS0, and this raffinate concentration treated feed is 2%, so which is 0.02. Okay, the question asked one here is, what is the minimum amount of solvent required? Okay, and question 2 is, if the amount of solvent used is 2.3 kg per second, how many stages are required? All right, in this case also it's possible that solvent required is say 1.5 or 1.2 times S min, then how many stages are required? All right, so different questions can be framed. Here first we are supposed to find out what is the minimum amount of solvent, and if we use 2.3 kg per second, which should be larger than S min, that's what we're going to check here, then how many stages are required. And we have been given this thermodynamic data. So again, some thermodynamic book or one of these textbooks, prescribed textbook, they give this this is also a very common system, pyridine, chlorobenzene, water, and here also we have pyridine, chlorobenzene and water. So now the data, maybe note down a few data here. So 0, 99.95, 0.05. Let's make an 11.05, 88.28, 0.67. Now we have 18.95, 79.9, 1.15. And let's skip some of the data here. Let's note down 35.05, 61.0, 3.95, 40.6, 53.0, 6.40, and we have 49.0, 37.8, 13.2. Okay. So looking at this data, amount of chlorobenzene here is larger. So you will expect that this is extract phase. Okay. And this water, so this is A, chlorobenzene, this is S, solvent, or B, and we have pyridine, which is C. Okay. And similar to this, we have some data here, 0.08, 99.92, 5.02, 0.16, 94.82, 11.05, 0.24, 88.71. Let's skip some of the data here. 44.95, 4.18, 50.87. Then we have 53.2, 8.90, 37.9, and we have 49.0, 37.8, and 13.2. Now look at before we plot, let's inspect here. Let's see that. So this is also C here. This is S. This is A. So essentially, this is your raffinate phase, and so this is X here for the solute, and we are using Y. Now look at the trend here. X here is smaller than Y. So 11.055, 18.95, 11.05. But at a higher concentrations, you notice that now X is greater than Y. That means you have the tie lines which will go like this for some part of the equilibrium phase before it starts flipping in the opposite directions. Alright, so this must alert us that del mean, we have to be careful whether the feed line which passes through this, it occurs this way, or the tie line which passes through this gives us del mean. Alright, we did say that in general tie line passing through the feed composition should give del mean, but then the possibility that some other del line, if extended, will give minimum amount of solvent required. So this is one example, a very peculiar system of pyridine, chlorobenzene, water, where you have this type of trend for some concentration range, lower concentration range. Say Y is greater than X, so we have the tie lines downward in this directions. Then we have X greater than Y, so the tie line in the opposite directions. Okay. Unlike in the previous example where we had all the tie lines in one directions, like this way or like this way. Alright, so let's come back to this problem here again. So again, based on these data, one has to plot. So let's see that again we use this rectangular system. So here we have 0, B 100%. So essentially we are plotting percentage amount of solvent. So instead of triangular diagram, now we are plotting this using this rectangular coordinates. So with X and Y here, and we have percentage amount of solvent. Now again, we don't have to plot all the concentration. Maximum maybe we have 60 here. So C is 60%. Okay. So here we have X and Y, and if we plot, then this phase diagram will look like this. okay, and somewhere here let's say this is 50. So again when we have the equilibrium diagram like 0, 10, say 20, 30, etc., and we are writing C here, that means this is a mole fraction of C in X or Y phase. So we have this raffinate phase and we will have this extract phase, okay, and the tie lines which will be coming appearing here, again you should make a note that the tie line will like this. Why? You have the situation like this, and then it's going to flip like this. All right, so one has to be careful. This is extract here, this is the raffinate. We have tie lines going in both the directions. For some concentration it's like slope downward, and here the slope is upward, okay. So again, instead of working on this rectangular coordinates, triangular coordinate system on graph, we are representing on this rectangular coordinate system with the percentage amount of solvent given here varying between 0 to 100%, and we are plotting solute concentration in raffinate phase and the extract phase, X and Y, okay. So the first question asked here was, what is the minimum amount of solvent required? That means we are looking for del min, okay. Now all we have to do is find that tie line which, if we extend through this feed concentrations. So here the concentration of feed was solute was 0.5. All right, so find these concentrations. So this will be in some iterations. You look for a tie line which, if you extend, then it intersects at 0.5, and if you do this, we have tie line extend like this. Now here again, if you go, we have 0% solvent, and R and P and corresponding to this X and P. So here we have this 2%, so 0.02, so 10% is 0.1, maybe somewhere here we have qualitatively with this 2%, not 0.02. So we connect this line and with this extend. This gives us, or should give us, del min, okay. If any other tie line, if you try to extend, you can see that this will go beyond this, like this, okay. There is also a possibility, now look at these two tie lines, or some tie lines in the lower concentrations for raffinate, that when you extend, so when you extend like this here and extend this line, this will also intersect somewhere here, and this may give you del min, corresponding to which we have this S min here. So now in principle we can have two scenarios, okay. Now I can recall previous examples. We had the equilibrium curve, and most of the all the tie lines, they were in one directions. So in this case, if you extend, you have the del min this way. If the tie lines are like this, monotonically decreasing in one direction, you extend through the feed, you have this del min in the left hand side. Here there are some tie lines on the lower concentrations and some on the higher concentrations where the slopes are different. So in principle, one has to calculate what is the minimum amount of del min, S min required for here, and what is the S min required from here, right? Any of these two will give you S min. You have to compare the two and find out which is the minimum amount, maximum of the two, so that when we take the larger amount of this, we are in the safer side. Now suppose you work on this and you calculate S min, okay, and now you take 1.5 times here. In that case, suppose the del operating comes to this side, okay. Now as long as del operating is here and all your operating line, they fall in this directions, then you are in the safe side. No circumstances that any of the operating line will be coinciding this. Similarly, if you work on this del min and you get S min here, and if you have the take 1.5 times larger than this, then you have del operating falling here, okay. So depending upon the amount of solvent which you use, now you can have the operating line going in this direction as well, okay. So this is the example where one has to be do some introspections and look at in what directions we have this feed concentration. In our problem example, it says that find the minimum amount of solvent required. Okay, so what we do here again, to find this minimum amount of solvent, say let's redraw this equilibrium phase diagram. So here we have 0.6 or 60%, and feed is say 0.5, 50% here, and the phase diagram looks something like this. Okay, we have the raffinate, which is 2%, so this is say 0.5, 0.4, 0.3, 0.2, 0.1, very small concentration here, let's say 0.02. So this corresponds to RNP, for which we have this XNP as 0.02. This is feed F given as, and for this we have the XF as 0.5 here. Amount of F is given to us 2.25 kg per second. All right, solvent is pure here, so YS is 0. Now if we connect these two lines, X and P and S, we have this is a straight line going in this directions. Now in this case, to find the del min, we find the tie line, let's say, which if you extend meets this feed concentrations. So as an exercise, some trial and error, take this tie line, you will see that this cross intersects at 0.48 compositions, and when you extend here, say it meets here, which is del min here. All right, so to find the minimum amount of S min corresponding to this del min, like in the previous example, we did this S over RNP, so the ratios of solvent to this raffinate phase will be equal to X and P dash del min. All right, over for RNP we have S over del min. So we can measure these two segments, lengths of the segments, but please notice we don't know the amount of RNP. All right, so unlike in the previous examples where we knew the amount of raffinate here. All right, so here, although we can measure the segment numerator and denominator on the right hand side of the equations, we do not know RNP. That means we should make use of those quantities, let's say F here. Now if we take 0. The tie line which passes through this and through this here, this will intersect at E1. All right, so here we have extract and here we have raffinate. This tie line which goes through this is, let's say we have Y1, which if you notice that this is 0.39. Okay, now how do we get this minimum amount of solvent? Let's see the schematics. We have the first and we have the last, so we can make overall species balance or material balance here. So we have F plus S min in this case equals to RNP plus we have this extract E1. Okay, so knowing this F and S min, so we connect this. Okay, so we are writing the equations that F plus S equals M, and we have E1 plus RNP. Okay, so we know the amount of feed here. So based on this F and S, right? So we have XM. We can find out XM. How do we find out XM here? Because the amount of solvent S is also not known to us. But remember, this is a tie line which goes through E1. If you connect this E1 with this, you will get here this point as XM. In other words, we are writing the mixing rule here, F XF plus S into YS. Of course, YS is 0 here, equal to E1 into Y1 plus RNP into XNP. So we know these compositions. We know these compositions. We know the coordinates composition here as well. We do not know the amount of S, nor we know the amount of RNP, but we know the amount of F here. Okay, so since we know this coordinate and we know this coordinate E1, with that's a tie line, in equilibrium tie line here, we have this Y1 and with this x1 we can mark this point. We can connect this, get xm, take this xm and connect with this S solvent here to again apply this mixing rule here. So first connect like this, then connect like this. Now we can find out what is the amount of solvent required. So we are writing again F plus S min equals E1 min plus RNP. Okay, and here if you look at an XM, you should be able to obtain this number as 0.3. That means now we can apply a tie rule. Say this location was F here for XF, and here we have S solvent which is YS equal to 0. If you connect this point here, we got this XM as 0.3. So all we have done, we connected this tie line again as E1, and if we extend this line here and connect this with this RNP, you have XNP as 2%. So first, instead of del point, now we are obtaining through this XM mixing point here, 0.3. Okay, so XM is 0.3. Then now we can write down F over S min. So F over S min is 0.3 minus 0. So this segment over 0.5 minus 0.3. So 0.5 is here minus 0.3 here. So this segment, and then this will be equal to, from here we can calculate S min. F is 2.25 divided by 1.5. So this number is 3 by 2, 1.5. We have 1.5 kg per second. So the idea was, how did we get this? Instead of working on this del min point, all right, we have calculated S min based on this mixing rule. In the previous example, recall, we located this del min, all right, but in that problem we could not find out S, because the earlier example we knew this amount of RNP definite, but in this case RNP is not given to us. So essentially we rely on this again mixing rule. We have the tie line which intersects the equilibrium phase at E1, connect this E1 to RNP to obtain this XM, and then we can apply again lever rule here between F and S to obtain this 1.5 kg per second. Okay. Now the second part of the question is, actual S is given to us 2.3 kg per second. All right. So the S min is, we calculated, is 1.5 kg per second. And now we have S as 2.3 kg per second. So now let us see where is the location of this del operating. So go back to the same equilibrium phase diagram. Okay, we have this 0.5 here, and now S min is 1.5 kg per second, and typically we calculate del min, and then we find out del operating. Generally it's given that it's 1.2 to 1.5 times del min here, but in this case now 2.3 kg per second per solvent is given to us. So again this feed is given to us. This is 2%, 0.02. We have the pure solvent. Extend this. Since the amount of solvent is given to us, we can locate this del point, del operating. Okay, so this example, again one can write actual S is 2.3 kg per second. We are adding with the feed here F, connect to this S, so we can get XM as F into XF plus YS into amount of S. YS is of course 0, F plus S. So we have 2.25 into 0.5 plus 2.25 plus 2.3. So that's the amount of solvent given to us. If you calculate, we have 0.246. So now we have xm slightly lower here. Now what is the idea of this xm? Once we connect with this 0.02 to x1, now we have E1 right here. Notice this corresponding to E1 min. Now we have the extract concentration which is smaller. Why? Because we have taken larger amount of the solvent. So it is a multi-stage, feed getting in here, raffinate getting out here. We have the solvent getting in here, and we have E1 leaving from this stage 1. So when we take the larger amount of S, the concentration of solute in this extract phase is smaller. So this had corresponding to our del min. Alright. And now we chose operating S larger than this 2.3 kg. So when you extend this line here now, you will see that this will intersect much ahead of. So if you extend this is a del min, and if you extend this, you will see that this intersects at del operating, and here you have this del min. So this is downward here. Now the question is, in this conditions, is there any possibility of certain tie lines coinciding with this? Now look at the tie lines which we said earlier, that all these tie lines, they are like this, and then they change the slope after a while in the opposite directions. So as long as we are here on the right hand side and del operating was towards this RNP, alright, then none of these tie lines is going to coincide with the operating lines, right? And if you extend these tie lines, they are on the left hand side. So there is no problem with any of those situations when we require infinite number of stages when the tie line coincides with the operating line. Alright. Had the del operating been on the left hand side, then of course then we would have to calculate del min based on these two tie lines, and then take this amount of solvent larger than this. So again, let's recall our discussions that location of the del, this moves when you take the larger amount of solvent in this directions till the line connecting this F and E becomes parallel to this. So that means we have reached minus infinity. If you take more amount of solvent, then the del points come on the right hand side, plus del. Take more amount of solvent, then you have del moving in this directions. So all the tie lines which are in this directions, this will give you 1 del min. You take large amount of solvent, you are here. All the tie lines which are in this direction, that will give you 1 del min. You take large amount of solvent, you have del operating. Okay. So in this example, we have seen that type of systems where we have both types of tie lines, slope downward in this direction and slope downward in this direction. Now coming back to the questions, now for this actual S equal to 2.3 kg per second, how many stages are required? So once we locate xm, from xm we locate the location of E1, then we locate del operating. Once you have del operating, you can construct the stages to find out how many stages are required. So for the last time, again we draw this curve, equilibrium curve like this. You had F 0.5, and then here you have 2%, 0.02. This is pure solvent. What we did, since the amount of solvent was given to us, we connected F with S. We got this xm 0.246, and then when you connect this RNP with this or XNP with this, you have E1. So now if you extend difference points, you get your operating del, then start making the tie lines, say E1. Here the tie lines were downward, so you get R1. First is connect with this del. Again you have E2. You find the tie lines slightly, they will start becoming flatter. R2, connect to this. You have E3. Okay, and when the E3, you will see now the tie lines have become exactly like this, and this will go below R and P. So we have stage 1, stage 2, stage 3. notice this what we were saying, that this peculiar system, certain tie lines at a larger concentrations or smaller concentration of raffinate, they are downward, and then a smaller concentration of expert, now you have these tie lines which are upward. Okay, so one has to do some introspection. Here the number of stages is greater than 2 or it is 3, so it has gone below this RNP equal to 0.022%. Okay, so that was example on multi-stage counter current extractions, where we try to find out how many stages are required and what is the minimum amount of solvent required. So it's a very peculiar example where we have two types of tie lines, and in which case del min can fall on the left hand side, del min can fall on the right hand side. One has to calculate the worst case. This example, S operating was of course given to us, so we were on the right hand side and we ensured that 2.3 greater than 1.6. We don't have that type of situations. Those tie lines which were sloped downward, they fell on the left hand side of the equilibrium phase. Okay, so similarly now we take one more example of this multi-stage counter current extractions before we conclude on this unit operation on extractions. So let's take one more example, slightly different from the previous two here. Okay, so here this problem reads that again in this case also we will do qualitative. You can do the exercise at your home and see whether you're getting the similar results. So we have 50% solutions of solute C in solvent A is extracted with a second solvent B. Alright, so reread the problem. All we are saying that we had one solutions which is C plus A, and we bring in contact with the second solvent B here. So still it is ternary system. We have A plus B plus C. C is the solute, A is our feed that becomes raffinate phase, and this B is solvent that gives us extract. Alright, it's given that the weight of B is 25% that of the feed. So B by F or A, it's given here as 0.25. So now it says the weight of B, all it means even the flow rate will be in the same ratios. So S by F maybe. Okay, so this is a solvent B that we have been using the previous nomenclature. S by F is essentially 0.25. So kg per second, and here we have also kg per second. So although it says the amount of weight of B, the weight of B is 25% that of the feed. Essentially this has the same meaning. S by F is 0.25. And the question asked here is determine the number of stages. Okay, determine the number of stages and the weight and concentration of the first extract if the final raffinate has 15% of solute C. So essentially this is X and P is 0.15, and then we can find determine the other quantities here. Alright, here notice that the solvent amount of S is not given, not the amount of feed, but the ratios is given. All it means, if you choose the feed as 1 kg per second as a basis, 1 kg per hour, S is 0.25 kg per hour. So this problem, feed is given, although the ratio was given, but we can always make choose a basis of feed 1 kg per second per hour to obtain the amount of solvent, which is 0.25 kg per hour. So there is solvent amount is already given to us. Essentially we will look for del and not del min, because here the S is already given to us. So this type of problem, all it means, again, if you do all kinds of balance, where instead of 1 kg per hour, if you choose 100 kg per hour, your solution will be in the same, S will become 225 kg per hour. You will get the same number of stages what you got in the earlier cases. Okay, so let's draw this equilibrium diagram. We have A, B, we have C, and let's draw this phase which will go like this. Okay, and say this is 10 here, this is 90 here, and we have, say, let's say 40, and then let's say this is 60. Okay, so in this case raffinate phase concentration is given as 15%. So if this is 90, 10 increasing this direction, that means somewhere here this is, we have to read this 85. Okay, so if you expand this, or we are saying that, let's say this is 0.85, then read like this. So just on this equilibrium phase you will have the line like this. Okay, so this is 0.15 is a solute, C is 15%, and how much is B and how much is A? So to obtain this B, again you look for the line which parallel to this. There's a B here parallel to this. You should be able to read a very small quantity here as 1% on this. So B is 1%, and how much is the amount of A? You will have to draw a parallel line to this, which will correspond to this on this scale of A to B here, which will be around 84%. So this 100% here, then you will have 90, then this is 80. All right. So in this case, you have to read this as 84%, 80, 90, and 100. So just an example. Sometimes you have to expand and read it very carefully. What is this amount of C? So again, going back to this problem, we apply this mixing rule. F xf equal to xm F plus S. Amount of solvent S here, or Ys is 0. So you have F xf plus S into Ys, but this is 0 here. So we can get xm as 0.5 into 1 kg over 1 plus 0.25 equal to 0.4. So mark this xm. We know the amount of the solvent here. All right. So all of this curve, again, we can mark on this. So the equilibrium phase diagram goes like this. Connect this F wherever it is, 50%, with the solvent B. Get your xm, mixing point here. We know this Rn, x and P. Connect this to obtain E1. And then you can find out, now again when you read this E1, you can see that this X is 58%. Alright, so this will be very close to 60. Okay, so the quantity increases like 100. This is 10 here. So this is C, 10, then 20, 30, 40, 50, 60. So if you read X equal to 0.5, so what you will do, you will take this to find the amount of solvent. You will read like this, that will be X.58. How much is the amount of B? You will draw a parallel line like this, and here you will read amount of B as 30%. So this B is 30%. How much is the amount of A? So you will have to look at the parallel line which goes like this. From here, A is 16%. All right. So all these numbers, when they report this is 100%, then there will be 90, then there will be 80. All right. So A is 100% here, and in this direction A decreases. So A is 16% corresponding to this point, B is 30% corresponding to parallel to this what we have read from here, or we can read from here as well. Okay, so X 58%, B 30%, A is 16%. Once we have located all 1, 2, 3, 4 points, now we can find this del L, right, operating line, and one can construct obtaining this del L, del operating. Then we can find the number of stages connecting with this, connecting with this, connecting with this. Here notice that there is no need for S min or del min. Generally we have said that del we need to know it's 1.2 to 1.5 times del min corresponding to this S min or del min, corresponding to this S min or S. Okay, so in this case the amount of solvent was given because the ratios of S to F was given to us. Although the absolute value of F was not given, we chose this basis of F. Why? Because again you go back to this mixing rule, we will have in the same ratios Ys into S equal to Xm F plus S. Alright, so just make a choose basis of 1 kg per hour, for which S is say 0.25 kg per hour, and then you can do this calculation here. Alright, so these are the examples we have chosen on counter current extractions. Okay, there are several examples given in the textbook, both Trebol as well as the book by Tata. Okay, you can go through them and try to solve all these thermodynamic properties, this equilibrium or solubility data. They may be given the textbook, or you have to look for certain other thermodynamic handbook there to find out on this extract and raffinate phase what are the concentration X and Y. And then depending upon the type of problem, either you can decide to work on equilateral graph, or you will like to work on this coordinate system, Cartesian coordinate system, or rectangular systems. In that case also you need the similar data, except that you have to modify a little bit to find out how does the XY mole fractions of the solute in the raffinate and the extract phase vary with the percentage fraction of solvent. Okay. So these are the 4 or 5 examples we have chosen in this unit operation extractions. There is one more small thing we would like to discuss here qualitatively. Just like in case of distillation column we had the reflux, it's also possible that in case of extraction we also have reflux. Okay, so generally typically in the industrially it's very difficult to maintain this reflux, unlike in distillation column it's very compulsory. So in case of distillation also, if you do some little bit more, go through this textbook, you have something called open system, in which case all we have, say, feed and solvent. One end we don't have reboiler, so all the time we have a steam. However, on the top we have a condenser, and then we have a reflux. Okay, so similar to that situations where you have the open system, so-called open system in distillation column, we can also have a reflux. So in other words, whatever extract comes out from one phase consists of A plus B plus C. You try to take out the solvent, or take out separate solute from the solvent, and send back your reflux at one end. Okay, so we would like to spend time here and see qualitatively how we can address this type of problem. So what we are trying to say here is that we have continuous counter current extraction with reflux. Alright, so essentially we can have a feed, say feed stage F, where feed enters like this, and then let's say we have a breakage here, and we have NP, last number NP stays, and we have a solvent which enters here. Raffinate is treated as RNP. So feed is making an entry somewhere here, just like in case of distillation column we have. So let's take a break here. Then we have another stage. So let's say this is first stage E1. We have extract E1. Okay. Now all we are saying that take this extract and separate the solute. So you have this E1 solvent separator here. Take this solvent and send back. So this is your solvent here, and this stream is solvent free stream. So essentially you're trying to recover the solvent here and send back like this. So you have certain amount of reflux. You can withdraw the product, let's say P, and you can have this raffinate as R0 reflux, which goes back in this directions. Okay, so this is what we have, situation very similar to the distillation column, where we had the condenser, and the top column we had the reflux going back to the distillation column. In this case also, with the solvent which comes here, we have a solvent separator. You take back, recover the solvent, and the solvent free stream is sent back to the first column. In this case, what we'll have, that this stream will be rich in solute or in C. So this section is actually your extract enriching section, and this side you have raffinate or raffinate stripping sections. Okay, so given this feed, again we are treating back, we are treating this to raffinate section, see RNP here. Here, what is the advantage? That amount of solvent required is smaller, or for the given amount of S here, the product we can have X and P much smaller than what we had in the previous case. Okay, so in this case also, the way you will have the treatment, it's very similar to what we had in case of distillation column. Now, if you record in case of distillation column, we looked for two difference points, del D and del W. Okay, so essentially you have the Ponchon-Savet methods, where you plotted HV and plot HL, and here you had XY, and then you look for one reflux here as del D, and then at the bottom you had del W. All right, so just qualitatively, if you want to address this extraction with reflux, one follows similar approach here. Now notice this, what we're plotting here is XY. So essentially this is your B over A plus B in two phases. All right, so in this case, in case of distillation, say you have liquid vapor phase and you have the liquid phase. So you have B, let's say more volatile, A plus B, and then here we have B over A plus B, top product and the bottom product. And what you plot here is a calorie per mole of A plus B, whether this is HV and this HL. Okay, now notice that one way of coordinating, if we try to make an analogy, we can also work on the system like N versus X and Y, capital X and Y. So what is capital X and Y in case of extractions? We are saying that C over A plus C. So here also we have two phases, similar to vapor and liquid. We have extract phase and we have raffinate phase. So we are plotting here C over A plus C, just like here we are plotting B over A plus C. And N is kg of B per kg of A plus C. So look at this, we have three quantities here, enthalpy H, and we have A and B. One can make an analogy, we have B and we have A and C. So H in energy enthalpy, this represents enthalpy of streams liquid phase and the vapor phase, A and B, the calorie over A plus B. Similarly, we can, from the same equilibrium diagram, we can also plot N versus XY. XY is C over A plus C. So no solvent here. So it's a solvent free C over A plus C. And here we can plot how much amount of solvent is required, B over A plus C, in two phases. If you do this, you will see that you will get the similar plot like this. So make what B we have is equivalent to what H we have, a scalar quantity, enthalpy in two phases. Here we have vapor and liquid, here we have extract and the raffinate, two phases. Here we have x and y, which is b over a plus b. Here we have c over a plus c. So we have the similar situations, and qualitatively one can show that you will have the same treatment. You will look for this del depending upon what was the reflux ratios in case of extractions. From the reflux ratios, you can get this f connected here, and one can find out again tie line connect with this, another tie line connect with this, etc. So this extraction with the reflux, it's quite uncommon. It's not that very popular here. It's very difficult to maintain reflux ratios or a constant reflux ratio in extraction system. Mind you, every stage in extraction consists of two small units. One is a mixer and one is a settler. All right. So to have a cascades of such type of units where you have a mixer and the settler, and then you want to separate at the end the solvent and send back your solute or solvent free solute back to this cascades of stages. Industrially, it's very difficult to do this, to maintain this purity here. But nonetheless, from the qualitative point of view, we can have very similar situations analogous to what we had in case of distillation column with open system, in which case we have one reflux at the top, and the bottom we have this open system, no reflux. Okay, so pure steam comes out from some other plant or some other units. So here also we can have a feed in the extraction, trains of cascades, feed enters somewhere here, and you take out this extract, make it solvent free, put on one separator, and send back solvent free solute or the streams in the opposite directions. And how do we do the treatment? We make an analogy. We plotted two ways of equilibrium phase diagram. One was A, B, C on a triangular. That's the most common. Then we said that, well, since A plus B plus C is always 100, it's one mole fractions. Then instead of working on this equilibrated phase diagram, we can also work on rectangular phase diagram. In that case, we plotted XY versus percentage B amount of solvent, or percentage fraction of solvent in the two streams. The third way is also plotting N versus capital X and Y. So what is capital X and Y? Solvent free, C over A plus C. And what is N? That's kg B per kg of A plus C. So we have A plus C plus B not distributed in different ways. We are plotting N versus X and Y. And if you do this, you will get a very similar curve like what we had in case of Ponchon and separate methods for distillation column. There we have enthalpy H over A plus B, and here we had B over A plus B. So we make an analogy. We have the scalar quantity enthalpy replaced by the amount of solvent. You will get the same stories here. You can look for the del point, find, and then connect the operating line and connect this tie lines to find how many stages are required when you have this extraction with reflux. Of course, extraction with reflux will give less amount of stages. We have large driving force if you fix the amount of solvent, or if you fix the number of stages, we can have larger purities. Okay, so this is the discussions we are closing today. Our discussion on this unit operation, the extractions. When we meet next time, we will take up a new topic that's on adsorptions. Okay, so far we have done absorption. We started with absorptions, then we had distillations, then we completed extractions. Now we will take up the next unit operation, which is adsorption.